to learn about some area. All right. So we're going to learn about all these other funky shapes and how to do their areas today, like trapezoids, kites, and rhombuses. Now, I kind of love that I can do this with this special board, but I want you to take a look at this particular trapezoid. Every trapezoid has two different bases and then has these like leaning sides. Now, check this out. Suppose I clone this. Okay, it's exactly the same, right? And now I rotate it all the way around, and I slide it right up to here. What shape have I made? It's a parallelogram, right? So what I'm going to do is, you're going to see this formula for the trapezoid, but what I want you to do is to realize how similar it is to the formula for just a parallelogram. Now, a parallelogram's formula is height times base. Now, in this particular example, what would my base be? It's kind of the addition of my two bases, right? It's base 1 plus base 2. And so if I was going to find the area of this, I could basically just do base times height. But remember, I'm only doing one of these trapezoids, not two of them, right? I only care about one of these. So then what would I have to put in the formula to get only one of them? Yeah, I would have to do half of base times height. And so it ends up looking like half of B1 plus B2 times the height. And that's kind of how the formula works out. Now, I'll tell you, sometimes what I like to suggest that students do is separate this portion of it and think of that as the average base length. And maybe that would help. So then you can think of this as, oh, it's just base times height, but since the bases are different, I need to average them out. Okay? And so here's your formula. I don't think it matters which one you call B1 and which one you call B2. It really should not matter. But I do like the idea that this is sort of the average of the bases. So here we go. We got a trapezoid. Let's see. I'm going to go ahead and call this B1. I'm going to go ahead and call this B2. So I do need the height. Wait a second. I have the height, right?
We don't.
Oh! Okay, we're going to pretend we don't see that. Watch. Here it goes. All right, we're going to pretend we don't see that. All right. I bet it's not 4. I bet I changed the problem and then I accidentally forgot on this to delete it. Okay, it would be a much easier problem if we knew that that was 4. Okay, so if we don't know that it's 4, what do we have to do?
You have to make a right triangle and you have to use the sign or whatever you want to use that and then move that over.
Exactly. As soon as you see that there is an angle in there that's like not 30, 60, 90, or 45, that should be automatically, you're like, oh my goodness, I need to do SOHCAHTOA here. So this is your height. Now, we need one more piece of information for my triangle. If this is 6, then this will also be 6. So how long is this? 2. Okay, so that's we got to think our way through that carefully. Now we can use the 47, the h, and the 2. And what trig function has that combination? Tangent, right? Because this is the opposite, and this is the adjacent. All right, so tangent of 47 is equal to h over 2. You'll do your cross products, right? This is just over 1. So your height is equal to 2 times the tangent of 47. And let's see, 2 times tangent of 47, I get 2.14. So that's my height. I'm not quite done with the problem, but I did find out that height. So now I can do the area formula. So the area is the average of the bases. What's the average of the bases? What's halfway between 6 and 8? So the area will be 7 times 2.14. And so what? I get about 15, approximately 15. I get 15.01 as my exact answer. So when you see trapezoids, don't forget that you can break them up into rectangles and triangles. Think about the different ways we could differentiate this. Instead of needing SOHCAHTOA, if this was like a 30 or a 60, you could do this with the ratios. If this was a 45, you could do this with the ratios. If I gave you the hypotenuse, you could maybe use Pythagorean theorem to find the height. Excuse me. So there's lots of different variations on this. And this is a perfect example of why studying for this final exam is going to be easy for you. Because right now you're studying, this is reviewing chapter 7. In chapter 7, we only had that triangle. But now that triangle is inside other shapes. All right, so let's talk about kites. Now, a kite, if you remember, the definition of a kite, I can use these, was 2 pairs of consecutive sides congruent. So like this is an example of a kite, right? Boom. Oh, that one doesn't, I forgot that one's not magnetic. Okay, there's a kite. Consecutive sides congruent, consecutive sides congruent. Here's the part that I can't remember if I kind of honed in on this point in chapter 8 or not. This is also a kite. What was that, Dennis? It's also you said it.
Rhombus.
It's also a rhombus, right? Because all 4 sides are the same. So it's interesting, rhombuses and kites are going to have something in common. So if we consider the area of the kite, one of the things we could do to kind of figure out where this formula comes from is to break it up into 2 triangles. So we could just look at the kite as the top triangle. And the top triangle's area would be 1/2. In this case, the base is AC. And the height is BE.
Do I have one brown pencil?
And if we wanted to, we could just add the area of this triangle. And that area would be, 1/2. The base is AC. And the height is DE. Now, do you notice that they have something in common? They share the same base, which is AC. So if we factor that out, notice they also share a 1/2. If I factor out the 1/2 and the AC, let's look at what we're left over with. We are going to be left over with a BE plus a DE. And then look back at this picture. What do you get when you have BE added to DE? What was that, Nicola? Yeah, you kind of get like the height, or it's like, what did we call this? Like the spine of the kite, the height, the diagonal, we could call it. So basically that entire line is summed up right here. So we could basically change this formula and make it such an easier formula if we call this one diagonal. And we call this the other diagonal. So essentially, we now just built a formula for the area of a kite using the lengths of its diagonals, or its spines, if you will. So here's that formula. A couple things to remember about a kite that will matter. Remember that these are always perpendicular here. And this triangle and this triangle are always congruent, right? And this triangle and this triangle are always congruent. They're always, right, there's all that symmetry going on there. All right, so let's try this out. So if we need to find the area of the kite, let's see, I can tell right away that one of the diagonals is a length of 6, right? This one here has a length of 6. So the question is, do I have enough information to figure out my other diagonal?
Yeah. 3, 4, 5.
I can figure out that that's 4. Because I know this is a right triangle, and I had the 3 and I had the 5. So now I know that my other diagonal is 14, and the area formula is pretty straightforward. So area is half of the 6 times the 14, so that's what, 42 units squared. Think about how this could differ. This was pretty quick because it was a 3, 4, 5. This could end up not being a triple, and you might have to do the Pythagorean theorem. This could be something where we give you an angle and you have to do trig. Okay, either way, you got to find that length of that diagonal. All right, so now when we look at rhombuses, we already know that it's a special type of parallelogram. But it also has 2 pairs of consecutive sides congruent, which also makes it a kite. So here's the nice thing about a rhombus. We have a choice of 2 different kinds of formulas. If we treat it like a parallelogram, what we can do is we can do area is base times height. If we treat it like a kite, we could use the diagonal formula. Area is half d1 times d2. So a rhombus, you kind of have a choice depending on maybe what information you have, or which looks easier. So those 2 formulas are on this slide right here, but I noticed we've kind of written them formally. Like this is diagonal 1, this is diagonal 2. All right, so you have a choice. You could do it that way. This is the base times the height. All right. Remember that it's always important that the base and the height are perpendicular. It could be drawn out here. Sometimes that can happen. Okay. So how about this? Do we have enough information? Let's see. I know that these are all right angles. Could I figure this out?
Yes.
Good. All right. So I would know that all the sides are 5. But I don't think I know what the height is. So let's try the other formula. If this is 4, tell me about this piece here.
4.
It's also 4. Oh, great. One of my diagonals is 8. If this is 3, how long is this?
3.
Also 3. So therefore my other diagonal is 6, and that's what I need in this case. So area is half of 8 times 6. So what, 24 units squared. All right, so remember with rhombuses, all these triangles are all exactly the same. For this one, we do have the height drawn in, but we also have information about one of the diagonals. Ooh, look up here. They told us one more little tidbit. If the perimeter is 52, I think we can figure out each side, can't we? How would I figure out each side? Divided by 4. So what is that? 13? All right, so this is 13, 13, 13, and 13. Okay, so I know my base is 13 at this point. That helps me. All right, so now let's look back at the picture, see what else. What about this triangle right here? That's 2 parts of a triple. So I can figure out that that's 12, which means this is also 12. I'm going to use the diagonal formula here. Even though the height's drawn in, I don't know what it is, but I do know what my diagonals are. So one diagonal has a length of 10. The other diagonal has a length of 24. I'm going to use that to find the area. So the area is half of 10 times 24. So the area is 120 units squared. Did I answer the question?
No.
Oh, it's still going, right? It's still going, because look at what the question was. The question was actually to go ahead and find this. But I can use the fact that I just found the area of this, and I know what the base is. Why don't I just call this x? I can use base times height. I can now switch formulas, right? Because I know I have 2 formulas that work, and I now know the area. So area is base times height. Bless you. I'm going to have 120 here. I know my base is 13. I called my height x. And now I can figure that out. So 120 divided by 13, 9.23. So that's what AE is. All right, so sometimes area is that bridge, that connector between 2 different formulas. That was a lot in one problem. Pythagorean triples, rhombus properties, 2 different formulas. The area of a kite is 80 square feet. One diagonal is 4 times as long as the other. Find the lengths of the diagonals. Okay, area is half D1 times D2. Okay, I know that much. I need to use the diagonal formula because it's telling me something about diagonals. All right, well, I do know the area is 80, so I can replace that. Awesome. Okay. Now, I still have 2 variables here. Is there any way that I could get them not have 2 variables?
Could you make one of them x and then the other one like 4x?
Yeah, let's do that. Let's make one of them x and one of them 4x. I like that. I don't think it matters which is which. So why don't we say that D1 is x and D2 is 4x. So then we would have an x here and we would have a 4x here. And we should be able to find that one missing variable. So we've got 80 is equal to, that's going to give me a 2 and an x squared. So 40 is x squared. So x is the square root of 40. Now I think that can reduce down a little bit, but it's going to stay a radical. I can reduce that, 4 times 10, 2 and 2, bring out the 2. Okay, so x is 2 square root 10. Awesome, I just found one of my diagonals. And then the other one is 4 times bigger than that. So one diagonal is 2 root 10. The other diagonal is 4 times that, so 8 root 10. And last but not least, if you get problems that have ordered pairs, this is my friendly reminder that you should just plot them. Anytime we've seen ordered pairs, if you plot them, it makes it so much easier. This is a rhombus. As soon as you plot it, you can very clearly see that its diagonals are horizontal and vertical lines. You can just count the boxes, right? This diagonal is 1, 2, 3, 4 in length. You know, this diagonal right here is 8. 1, 2, 3, yeah, 8 in length. What if the diagonals, after you plotted it, what if the diagonals were not horizontal and vertical lines? What would you do then? Bingo. So do watch out for that. So if the diagonals are not horizontal or vertical, use the distance formula. Because you would need to use that to find, you know, the length of a line. Or maybe when you plot it, maybe what you need to look at is the base horizontal and the height vertical. Okay, look for a horizontal and vertical combination somehow. Distance formula is square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. In case you've forgotten it. All right, folks. I am done downloading.